Good morning, everyone who is in Bandung in Indonesia. So also good afternoon or good evening for everyone around the world. Thanks for joining us today. In this session, we will have a lecture from Professor Masashi Chiba. He will talk about dark matter controversy, especially in a local group and also in a Milky Way. So before he give a lecture, I will introduce you about his short CV. Now, Professor Masashi Chiba is a professor in Astronomical Institute, Tohoku University. He got his bachelor and a doctor degree from Tohoku University, and his research interests, so many research interests. Maybe I can mention some of them: galactic archaeology, hemodynamical evolutions, galactic dark matter, also about observational cosmology. So now I wanna welcome Professor Masashi Chiba. Please, times is yours.
Okay, thank you very much for introduction, Anton. And Anton was actually here before and got PhD degree here. So he's supposed to be very familiar with this university and the life here in Sendai. Okay, let me share my screen. Can you see? Can you see this screen?
Yes, we can see it well.
Any problem? Is it okay?
Yeah, is it okay? We can see it clearly.
Okay, so let me start the lecture on title is Dark Matter Controversy in the Milky Way. It's a big title, and okay, this is the lecture one. Before starting the lecture itself, let me briefly introduce where is our university and where is Sendai. Okay, Tohoku University, Sendai, Japan. Sendai is here. It's in the north part of Japan. Okay, Sendai is here, and actually, this map shows the epicenter distribution of the earthquakes, which occurred 9 years ago. It's very how to say huge, and magnitude is almost 9. So a lot of people died, mainly due to tsunami. 20,000 people died due to this earthquake. And here is Sendai City and the Pacific Ocean. And the Sendai Station is here. And our campus is somewhere here. And this pink region, this region was actually affected by tsunami, as shown here. And so many people died living this region, but our campus is far from this area, although it takes only 20 or 30 minutes by car. But anyway, we were safe. And current status at Tohoku University, we have totally recovered to operate our education research activities as usual, of course. There are a lot of damage after earthquake, but after restoration, now it's a usual life. Daily life goes on as usual in the city. And radiation level in Sendai, you might be worrying about some effects of the say radiation, but Sendai and the Fukushima as well, I should emphasize, radiation level is pretty small, less than half of the world average. So for detail on our university, please visit our YouTube channel shown here. Okay, back to lecture. Okay, lecture one. Lecture one deal with some introductory topics on dark matter. So I think it's not so difficult to understand, I hope. So title is Dark Matter in the Milky Way and Unsolved Issues. And the introduction and evidence. I'd like to show evidence for dark matter in the Milky Way. And what is the total mass of the dark matter in the Milky Way? What is the global shape? What is density profile? Are there any substructures? And lastly, I like to summary. And as I said, this lecture one is quite introductory. So, so I hope many people understand the the dark matter, current status of dark matter in the Milky Way. And lecture two, I'd like to show our recent work on to solve the, some paradox in the currently facing the paradox as I show in my lecture. Okay. Okay. First, as an introduction, I guess many of you already know, but let me remind you that there is very robust evidence for dark matter in the Milky Way. Okay. This is the rotation curve of the Milky Way. It's made by, the measurement is made by spheroidal, is our Chiba's colleague. And it is a distance from the galaxy center, and there is a rotation velocity. And provided that the orbit is circular, then the rotation velocity reflects the background gravitational potential, as you know. And you see the, okay, sorry, the sun is around at 8 kiloparsec. And as you see, the flat rotation curve is generally flat. Okay. And this is a very known observational result. And if the mass distribution is spherically symmetric, this is a very important assumption. In reality, mass distribution is not spherically symmetric. So this simplification is not achieved in the general case. But if spherically symmetric assumption is made, okay, this is very important. But anyway, then the centrifugal force is balanced with the gravitational force. And so supposing rotation velocity is constant, then the mass...
excuse me, Professor Chiba, the slide is still in the current status at Tohoku University. What we see here.
Say again?
Yeah.
Can you see the
this slide?
Screen?
We cannot see your slide about. This is still in current status at Tohoku University. In
oh, really?
What we see? Yeah. Okay. Yes.
Can you see it? Can you see the rotation curve?
I can see. I can see it.
I can see it.
I can see from home.
Okay. So okay, rotation curve. Okay. So maybe should I repeat? Okay. This is a rotation curve. Okay, let me briefly repeat what I said. this is a rotation curve, and as a function of the distance from the galaxy center, and rotation curve is basically flat. So V lot is nearly constant. And okay, the rotation velocity reflects the gravitational force, and if one assumes the spherical symmetric mass distribution, this is very important assumption, although in reality mass distribution is not spherical symmetric. But anyway, then if this assumption is made, then the centrifugal force is equal to the gravitational force, and here the mass is total mass inside the given radius. Then the supposing rotational velocity is constant, then the mass within the certain radius is proportional to r. So this suggests the presence of dark matter halo in the Milky Way. Okay, the next page. Can you see this screen? The dark matter in external galaxy. Okay, so okay, here the another example is now it's in the case of an external spiral galaxy, NGC 3198, and here shows a stellar disk surrounded by extended H1 disk, shown in the white contour lines. And right panel shows the rotation curve, and this marks show the data. And as you see, the rotation curve is again nearly flat. And this rotation curve cannot be reproduced from the disk component because this components, the extension of this component is finite, so gravity decreases with radius. So we need some extended the density distribution, the halo, to reproduce the mass this rotation curve. And this rotation curve again reflects the mass inside the given radius, basically, if the mass distribution is spherically symmetric. So in this case, the rotation velocity at r is given in this formula. So it's very simple. Again, I emphasize that this is written when the mass distribution is assumed to be spherically symmetric, but generally it's not. Okay. So next page is show the several other cases on the external spiral galaxies, and it is apparent other spiral galaxies also show generally flat rotation curve. There are some how to say disturbance, probably due to spiral arm and so on. But anyway, the general rotation curve is flat, so we need a dark halo surrounding this component. Okay, so but this method, to determine the mass distribution based on the rotation curve, is limited because dark halo is actually much larger than the size of the galactic disk, where rotation curve method is applicable. So real dark halo is much larger, so it is not possible to apply the rotation curve method to determine the mass outside the disk, apparently. So we need other tracers. What kind of tracers? There are a lot of stars, actually 10 billion stars, so-called field halo stars. And there are about 150 globular clusters and about currently 80 satellite galaxies, and they are orbiting within the dark halo space. So the spatial motion, basically dominated by random motion, reflect the gravitational potential of the dark halo. So by analyzing this random motion, basically random motion of the halo traces, one can determine mass information on the dark halo. So as I said, the rotation curve method is limited only in the inner part of the dark halo. Okay. Okay, so here, okay, I was talking about the Milky Way dark matter halo itself, and this is on the dark matter stuff associated with Milky Way satellites. I will show more detail later in this lecture 1 and also lecture 2. Okay, most of the satellites are so-called dwarf spheroidal galaxies, dSph. And these galaxies have no gas, and star distribution is so diffuse. These are example, Sculptor, Carina, Phonax, and so on. They look so boring, but they are so very important because they are very, very dark matter dominant, as I show later. And stars here, there are some stars. Yeah, for example, Leo 1 is so diffuse. And each of the stars show a random motion. And the random motion is up to 10 kilometers per second. And total stellar mass is 10 to the 4 to 10 to the 6 solar mass. So, okay, so this random motion is, you might think it's small, but it's compared to the total mass of the stars, it's quite large. So self-gravity of the star system alone cannot bind member stars. So in this Milky Way satellites, we need a dark matter, and actually massive dark matter needed to bind these stars. So as I said, these galaxies look so boring, but they are so important to study dark matter or nature of dark matter. Actually, this shows dark matter in the Milky Way satellites again. X-axis, the V-band absolute magnitude of each dwarf spheroidal galaxy, actually Milky Way satellite, and Y-axis is mass ratio between dark matter and stars. So it's a total mass to luminosity ratio. And as you see, the fainter the galaxy is, more dark matter fraction. And actually, mass to luminosity ratio is reaching in this range up to 10 to the 3 or 1,000 or more. So more faint galaxies expect to have more dark matter. So basically, these Milky Way satellites are very, very largely dark matter dominated, although there are only few number of stars. So it is very, these satellites are very important for the studies of dark matter. And as I said, I will show some details on these satellites later. Okay, so I expect you already learned some dark matter candidates. Okay, probably, yes. There are roughly two candidates. One is a faint compact stars, such, made of Baronic matter. So Baronic matter, what is Baronic matter? It's a normal matter made of protons and neutrons. And candidates, compact stars are brown dwarfs, white dwarfs, neutron stars, and black holes. And also nowadays, a lot of discussion on primordial black holes. Primordial black holes are not made of Baronic matter, but anyway, black holes. Primordial black holes are also the probably in this group, faint compact stars, and these are so-called MACHOs, massive compact halo objects. Sounds very strong. And on the other hand, the elementary particles such as neutrino, neutralino, photino, action, they are dark matter candidates, and they are so-called non-barionic matter. And the most interested dark matter candidate particles is so-called WIMPs, weakly interacting massive particle. And especially we are interested in massive particle in small random motion, and say each of the particle mass is GeV or something. And most representative case, the dark matter model is a cold dark matter, such as neutralinos. And this latter one candidates are more promising. There are a lot of topics related to faint compact stars, but since the time is limited, I'd like to omit. And in my lecture, basically dark matter candidates are supposed to be made of elementary particles, and I'd like to talk about some issues related to this scenario. Okay, as you know, probably you learned already in this summer school, based on the dark matter models, structure formed from small scale to large scale. Okay, and this is a simulation result, and as a function time, the structure formed. And so a small scale halos form first, and then large scale structure from subsequently through merging and accretion. And this theory successfully reproduced observed large scale structure. This slide shows this success of the cold dark matter theory as a function of the spatial scale, and the y-axis is density fluctuation, observed density fluctuation, including the fluctuation in cosmic microwave background, and galaxy clustering, gravitational lensing, and spatial distribution of intergalactic hydrogen. And this blue maybe cyan line is a prediction of lambda CDM. Lambda is, I suppose you already learned, is lambda cosmological constant. So lambda dominated CDM model predicts this line, and it's naturally explain the observed large-scale structure of the universe. So this cold dark matter theory is quite successful, but there are a lot of issues in the very small scale, say galaxy scale or Milky Way satellite scale, as I'll show later. So, but beyond this small scale, say beyond 1 megaparsec, the cold dark matter theory is quite successful for reproducing the large-scale structure of the universe. Okay, this is kind of the introduction to lecture 1 and also lecture 2. And let me move on to some detail of the dark matter halo, dark matter in the Milky Way. Okay, this is this shows. Okay, so let me show total mass of the dark matter in the Milky Way, and this shows the velocity distribution of stars near the sun. And the x-axis is basically velocity in the azimuthal direction, so rotational velocity. 0 is here. The y-axis is the other velocity component. And this dot shows the data, and this circle shows total constant total velocities. So to bind all the stars, okay, escape velocity of, as I said, these are stars near the sun. So escape velocity at this position near the sun should be around 500 to say 550 kilometers per second. Unless otherwise, the stars are not bound to the Milky Way. So, basic assumption is that all the stars are bound to the Milky Way gravitational potential, and the maximum velocity is nearly the escape velocity at the position of the sun. So, given this escape velocity, we can set limits on the gravitational potential at the position of the sun, because escape velocity can be very easily written using gravitational potential phi at the position of the sun. So escape velocity can set limits on the mass or gravitational potential. So you know, the escape velocity of the Earth. The usual lecture, I try to ask some questions, some student, what's the number, what's the escape velocity of the Earth, but usually they can't answer. So anyway, please check what is the escape velocity of the Earth. Okay, so escape velocity is a very important, useful information to set limits on the depth of the gravitational potential. On the other hand, the rotation curve, it's a rotation curve set limits on the mass distribution and mass of the Milky Way, but it's through the balance between centrifugal force and gravity. But in this case, the limits is on the depth of the gravitational potential. Okay. So, but it is okay. Okay, this is just only applied to the solar neighborhood. But it is ideally it is better to have more the sample at larger distance from the sun, and we like to set limits on the escape velocity and gravitational potential over the Milky Way. So limits on the gravitational potential at other radii based on rest frame observability of distant sample, and observed rest frame velocity of the distant sample should be smaller, equal or smaller than the escape velocity at that position. So this kind of work is made, 17 years ago, okay, already. It's done by my former student, Sakamoto. Okay, this is very simple analysis. First, we assume the gravitational potential here, and parameter is A, and the mass. M is the total mass of the halo, which provides gravitational potential, given here, and corresponding mass distribution of the dark matter is assumed to be here, and A is actually here in this. Okay, when the R is smaller than A, its rho is inversely proportional to R square, as I mentioned from the rotation curve. But in the at large R, rho rapidly decays. So A is actually corresponds to the size of the dark matter halo. Then given the A, one can obtain the mass, total mass M. Okay. So A is parameter. So case 2 is first. Let's suppose A equals 20 kiloparsec. Then this is the diagram. The x-axis escape velocity obtained from this model, just 2 pi, root of 2 pi as a function of R, and the y-axis is observed rest frame velocities. But okay, I should show. Sample is satellites, globular cluster, and blue horizontal branch stars. They are distributed over our Milky Way halo. And field marks show objects with proper motion data at open is without proper motion. So open marks show just a lower limit for the rest frame velocities. But anyway, okay, so field marks, we have three-dimensional velocities. So anyway, so all the objects should be in this part to, okay, unless otherwise, these objects in this side are not bound to the Milky Way halo. So when A is 20 kiloparsec, then we fail to bind these objects, so it's rejected. But if A equals almost 200 kiloparsec, then we nearly succeed to bind all the objects. And Draco is one of the dwarf satellites. Palma 3 is a distant global cluster. Okay, and Leo 1 is one of the dwarf satellites, and it has a very large dinosaur velocities. It's one of the key objects to bind to set limits on the mass of the Milky Way. But anyway, it's a very straightforward analysis. So at least we need A as large as 200 kiloparsec. So in this way, one can set limits on the basically the mass of the Milky Way. But it's so simple. But probably it's better to adopt a more sophisticated method. Here's a okay, I like to skip the detail, but this is based on the maximum Reichmann method to maximize the probability that the observed stars at the each position. And in this analysis, distribution function, the stars are assumed to be simply here, given here as a function of energy and total angular momentum. And basic parameter is velocity anisotropy parameter. It's expressed velocity anisotropy and defined here, beta parameter, so-called. And so when beta is larger than 0, then velocity is radially anisotropic. And in the case of negative beta, velocity is tangentially anisotropic. So as I said, Leo 1 has a large velocity, so so Leo 1 affects somehow the mass estimate. But anyway, the even concerning Leo 1 or without concerning Leo 1, we arrive at kind of the universal results here. And result is expected as like this. Total mass is around 2.5 times 10 to the 12 solar mass over the size is 200 kiloparsec. On the contrary, the visible mass or luminous mass is 10 to the 11 solar mass over 15 kiloparsec. So we see only 10% of the total mass. So okay, this is a result we obtained almost 17 years ago. What is the recent result? So there are a lot of work recently, especially using Gaia proper motion. Gaia is, you know, the astrometric satellite, second astrometric satellite launched by ESA in Europe, and the Gaia provide very precise astrometric data, parallax and proper motion of billion number of stars. So there are several works using Gaia data, using stars, or this case is global clusters. Okay, let me show just the final result. Okay, these people arrive at this number. Okay, it's small, but the order of 10 to 12 solar mass. And as you see, here the mass inside certain radius this shaded region is the results using Gaia or some other data, common other data. And the colored error bar is the previous result. And the previous results nicely follow the recent results. And as you see, I'm happy to find our work 70 years ago, Sakamoto et 2003. And it's difficult to recognize where is it. But anyway, it's consistent. And there are also other recent results. Well, there are some difference in these factors. It's from 1 to 2, but the order is basically 10 to 12. And the total mass of the dark matter halo in the Milky Way is not larger than 2 times 10 to the 12. Yeah, say not 3 times 10 to the 12, not 4 10 to the 12, 10 to the 12, just between 1 and 2 times 10 to the 12. Okay. This is very important. Okay, next, let me move on to the global shape of the dark halo in the Milky Way. Okay, to understand or to determine the global shape of the dark halo, one good tracer is stellar stream, as I show right now. And regarding a stellar stream in the Milky Way, the main source of the stream is this one, Sagittarius dwarf galaxy. This dwarf galaxy discovered 1994 in the direction of Sagittarius, and this is the core region of Sagittarius. And this Sagittarius galaxy, okay, here show galactic center, the sun, and the Sagittarius dwarf. Sagittarius dwarf is the closest satellite in the Milky Way. So since it's so close, it's subject to tidal distortion. And so there are a lot of discovery papers on the stellar streams originating from this Sagittarius dwarf galaxy. This is actually the Sagittarius stream over the sky, and this is the Milky Way galactic plane. Sagittarius is here, and this is the north hemisphere and south hemisphere, and this shows the distribution of stars in the halo region, and the colors reflects the distance. But anyway, they are very large scale stream like feature, like a jet stream, and here also, and the source is Sagittarius dwarf galaxy here. So it's a so-called Sagittarius stream. And this stream is very important and interesting. And this Sagittarius stream is found to be distributed over the space of the Milky Way. It's like a ribbon. And it is found that stream is not exactly, but it's nearly confined onto a kind of some flat plane. It's so-called orbital plane. It suggests that the dark halo is rather spherical or round in the radial interval where such a stream is recognized, say 15 to 60 kiloparsec. Why? there's some simulation to reproduce this Sagittarius stream, and this is work by Johnston, 2005, and this is a stream or tidal debris from the Sagittarius, and key parameter is the ratio of the gravitational potential, or ratio of the mass which provide the gravitational potential. Q phi is a actual ratio of the gravitational potential, and Q rho is the corresponding axial ratio for dark matter density. And if the mass distribution is nearly spherical, then, as you know, the angular momentum is conserved so that all the orbits are confined within the flat two-dimensional plane, so orbital plane. So basically, all the tidal debris are confined in the original orbital plane of the Sagittarius. So the stream is very sharp, as observed. But if the potential is deviate from the spherical symmetry, then the orbits also deviate from the orbital plane. So the stream is seen very diffusive, and it's not in its disagreement with observed distribution of the stream, actually. So to reproduce the observed sharpness of the stream, Q phi in between 0.9 and 0.95, or mass, okay, around 0.8 or 0.9. So it's nearly spherical. Unless otherwise, we can't reproduce the thickness of the stream. So the stream, which distributes over the space of the halo, is a very ideal tracer of the shape of the gravitational potential of dark matter halo. Okay, so as I said, it's nearly spherical. But I said that the standard theory for dark matter candidates is called dark matter model. And halos are formed hierarchically. So, but visualized so-called cold dark matter halos are generally triaxial or prorate. It's first proposed by, shown by Jin and Stowe 20 years ago. This show visualized dark matter halos in the several mass scale. And here show ABC is a mass ratio. It's a A over C is okay. The ratio between the major and minor axis. So okay, forget about the detail. In essence, the cold dark matter halos are generally triaxial, correct? Not spherically symmetric or round. So observed dark matter halos, shape of the dark matter halo is not consistent with this suggestion. Okay, but point is that this simulation is basically, not basically, totally dimensionless. So this simulation doesn't consider the effect of gas or stars, I mean baryonic component. If one considers the displaceable baryonic component, then gas cooling makes the dark matter halo rounder. Okay, this shows the dashed line. Okay, this is x-axis radius with the unit visual radius, and the y-axis the mass ratio, axial ratio. Sorry, and the thing is upper panel is for cluster scale, lower panel is galaxy scale. So let's take a look at lower panel. So dissipationless dark matter only simulation show this very flattened dark matter halo shape. But if one consider, okay, again, forget about, oh, no, sorry, the blue one is cooling is considered. So where the baryon is mainly the gas, and the red one is also considering the stars. But anyway, forget about the difference between the red and the blue. Anyway, the cooling can make the dark matter shape rounder. This is simply understood because after cooling, gas can fall into the center of the gravitational potential, and it's like how to say mass is concentrated in the center. So gravitational potential is let's say kind of the Keplerian potential. So it's a spherical symmetric. So this enfolding baryonic component can makes the very flat or triaxial gravitational potential shape rounder, which is consistent or in agreement with observed roundness of the dark matter halo in the Milky Way. Yeah. So there's solution to to be consistent between the cold dark matter theory and observed roundness of the dark matter halo in the Milky Way. But beside the region where such a semi is observed, we don't yet understand the real shape of dark matter halo. So we really need more analysis based on the more other stream stars, although other stream stars are small scale, so compared to a Sagittarius stream, but it is very important to consider other streams and to set limits on real dark matter shape of the Milky Way. Good. Okay, next, I'd like to move on to the density profile of the dark matter halo in the Milky Way. Okay, as I said, the Milky Way halo, as well as other spiral galaxy, shows spherical is also, sorry, constant rotation curve as a, okay, V lot is constant. So again, if the mass distribution is spherical symmetric, rotational velocity can be written in this way at each radius. And when we assume rotational velocity is constant, then, as I said, the m at within the some radius is written in this way, and this mass is proportional to r when v lot is constant. In this case, rho is inversely proportional to r squared. So it's correspond to a singular isothermal mass distribution. So yeah, but in the Milky Way case and also other spiral galaxies, this disk region is so dominated by other components than dark matter. I mean, stars and gas. So stars and gas are dominating. As you see from this rotation curve, disk dominates the rotation velocity compared to halo. So it is not ideal to derive the density profile of dark matter alone from this baryon-dominated dark matter Milky Way or other spiral galaxies. Okay, what is the prediction of the cold dark matter models? This shows the evolution of the three dark matter halos time goes on like this, and the three dark matter halos having a different merging history. Okay, the left one, dark matter grows very slowly. Middle one, this dark matter is basically made of major merger here, and this dark matter halo made of many dark matter small halos. So, but at each epoch, dark matter halos are in the dynamical equilibrium somehow, and it's so-called realized dark matter halos. And this dark matter halos show kind of universal profile discovered by Naval Frank White, and it's so-called NFW profile. And this is a functional form of this profile. And RS is some typical scale. And at smaller radii, rho is inversely proportional to R. So it's a so-called cusp. So it's infinite at R equals 0. So it's a cusp. And at the larger radii, it's a rapidly decrease. Yeah. So this cusp density profile is a natural prediction of the dark matter models. Okay, this is the original result, but later people work suggests some different results. For example, Ben Moore said this density profile with index gamma, say rho is inversely proportional minus gamma, then the gamma is not 1. Gamma 1 suggests NFW profile. But Moore et al. Said gamma is not 1 but 1.5. So this is the result by Navarro et al. 2004, where the inner density profile is NFW or Moore et al. Profile. And actually, the result is there's no universal gamma. The gamma is changing with radius, and it ranges from 1 to 1.5. Here shows the result for 3 mass scale, dwarf, galaxies, and clusters as a function of the radius from the center of each dark halo. And y-axis is minus gamma. So, okay, let's say, let's take a look at the galaxy scale. Okay, so gamma is not universal, it's changing with radius. And okay, so, and the solid line is for NFW case, tending to -1. Dotted line is tending to -1.5, so a Moore profile. But the actual simulated dark matter halo is in between, as you see, and it follows this this line, dashes dotted line, and this line suggests the gamma is not constant at the very inner part, but it's continued to be dependent on R. And this line is so-called INAST profile, originally proposed by INAST for in a different context. And it's a bit complicated density profile, but this nicely reproduces simulated density profile. And this gamma is no longer constant, but it's changing with radius in between 1 and 1.5. But anyway, whatever profile, important point is that density profile is cuspy. Yeah, in the center. This is a projection of the dark matter models. But there's a so-called core cusp program. What is a core cusp program? What is core? Okay, this is show core. Okay, this is a density distribution of the dark halo as a function of the radius. NFW or Inus case, Inus profile, it's show cuspy as I explained, but core dark matter profile is like this. It's a rather flat density in the center. Okay, so this is a rotation curve of, it's not Milky Way, but external dwarf galaxies, gas-rich dwarf galaxies, say dwarf spiral galaxy. And this gas-rich, so rotation curve is derived. And this shows the data, DDO, these numbers, and as a function radius. And NFW prediction is like this, because NFW is cuspy, so that at given radius, gravity is larger than core case. So the centrifugal force should be larger than core case, so that rotation velocity should be larger than core case. So NFW case, the rotation curve should like this. So in contrast to the observed rotation curve, and the observed rotation curve is well fitted to the core case. So from this observation, these small galaxies have a coord dark matter profile, contrary to the CDM model prediction, say cuspy dark matter profile. This is so-called core cusp program. Not only the galaxies having interstellar gas, our Milky Way satellites dominated by dwarf spheroidal galaxies, as I say, dSph, which have no gas. They don't show a circular rotation. They show basically a random motion. But this random motion also reflects the dark matter density profile. So this shows some example of the density dispersion profile for several dwarf spheroidal galaxies, say Draco, Ursa Minor, Sculptor, and Phonak, so on. It's made by Walker et al. This R is distant from the center of each dwarf spheroidal galaxies. So it's 100 to 1 kiloparsec. And density dispersion of the stars is, as I said, of the order of 10 kilometers per second. So using this density dispersion and density dispersion profile, and given the assumed dark matter model like this, where in the inner part of the halo, the index density profile, slope density profile is given by gamma 1, and given the star distribution, and with the James equation for its basically mechanical equilibrium, dynamical equilibrium equations, then one can derive the limits on this density profile. And it turns out some dwarf spheroidal galaxies have core profile. And this topic I will show in the lecture 2, okay? So anyway, even these dwarf spheroidal galaxies dominated by random motion stars suggest a coord dark matter profile in some dwarf spheroidal galaxies. So they are inconsistent with the CDM model prediction. And regarding density profile, there's another program with our attention with the prediction of the cold dark matter model. It's so-called too big to fail program. This is just complicated and busy slide, but anyway, this shows this shows the simulation result, numerical simulation for the basically a density profile of the subhalo, small halos within the host dark halo, like Milky Way dark halo, expressed in terms of the circular rotation velocity. Okay, and as I said, the circular rotation velocity is basically reflect the, it's too distant. Oh, sorry. Yeah, here. Yeah, circular velocity reflects the mass inside R. So instead of plotting the mass, rotational velocity or circular velocity is also the express the mass distribution. Okay, sorry. Okay, can you see this one? Okay, so this is 6 examples, 6 Milky Way like dark matter halos, and each curve shows a rotation curve of most massive subhalos. The solid line shows the most massive 10 subhalos rotation curve for 6 liquid type halos. Compare with observed observationally determined circular velocity for luminous galactic satellites. So field circles show galactic satellite rotation velocities at their half-light radii. Okay. So apparently, simulation results show much larger circular velocity, meaning that the mass inside this radius is larger in the simulated subhalos than the observed one. So in other words, most massive subhalos in the lambda CDM simulation are denser, or having more mass inside R than those in most satellites. This is so-called too big to fail problem. So this discrepancy is one of the serious issues to understand the origin of the satellites and also the nature of the dark matter. Okay, lastly, I'd like to talk about the substructures in the dark matter halo. Okay, dark matter halo. This is a simulation result for the Milky mass halo by Baruch and Boyler-Coltin. Okay, this is a typical dark matter halo for the Milky Way mass, 10 to the 12 solar mass, and white dots show the dark matter particles. Although real dark matter is black, but it's shown with the color, the white color, and radius is about 250 kiloparsecs. It's a kind of video radius with the Milky Way mass halo, and there are a lot of substructure or subhalos, so-called subhalos, the small scale dark halos with mass 10 to the 6 to the 10 to the 9 solar mass. There are actually hundreds of subhalos surrounding the main part of the Milky Way dark matter halo. So if the stars form and galaxy formation occur within all of the subhalos, then we expect this number of the luminous satellites. But observed Milky Way satellites, as I said, only about 50. Here shows some special distribution of the known Milky Way satellites compared with the Milky Way disk shown with gray, and the color means some difference in the Milky Way satellites. But anyway, this size corresponds to the brightness, absolute brightness of the satellites. But anyway, the satellites are distributed in the Hale space, but only 50 satellites are known. So this is so-called, this discrepancy is so-called missing satellite problem. So to solve the missing satellite problem, some people adopt alternative dark matter models such as SIDM or warm dark matter and so on. SIDM, I'm wondering other lecturers already explain the nature of some properties of the candidate dark matter models. I don't know, but anyway, SIDM is a self-interacting dark matter models. And based on this model, the predicted dark matter density profile have core here compared to a CDM prediction. So it solved the core cusp problem. Why the SIDM shows a core? Because it's due to self-interaction. Self-interaction makes the cusp is smoother and cored. Okay, but in the case of the warm dark matter, in this case, the mass of each particle is of the order of keV. Warm dark matter case also show a cuspy dark matter density profile. But in the case of warm dark matter, this is the predicted distribution of subhalos. The only small number of subhalos comparable to observed number of the luminous satellites. So if one adopts the warm dark matter theory, then one can reproduce the observed number of the luminous satellites. So there's no missing satellite problem. So depending on what kind of the dark matter models, one can solve missing satellite problem or core cusp problem and so on. Some detail I would like to show in lecture 2. Okay, so there are missing satellite problem, and there's some mismatch between the number of the luminous galaxies, satellite galaxies, and predicted subhalos, number of predicted subhalos. So apart from the Milky Way, are there any evidence or signature of dark matter substructures? If there are substructure, dark matter substructure within the Milky Way, those substructure would give the dynamical effects on the visible galactic structure. Say, star cluster may be destroyed, or stellar stream might be affected. And there's some evidence recently using Gaia that in the Milky Way there's some subhalos which affects the visible streams. Also, when these subhalo orbiting and collide with galactic disk component, then the stellar disks are affected by these subhalos and subject to dynamical heating. This process might for example, thick disk component. Okay, but although I don't explain the detail. And second probe is gravitational lensing. Well, there are a lot of experts here, including Anton, Primadi, So for detail, please ask them. Okay, if the density distribution is not smooth but having a lot of substructure, then the observed lens image are affected, so-called anomalous flux ratios, or some extended lens images are affected due to this small substructure made by dark matter subhalos. So, okay, first dynamic effect. This is the simulation result. Okay, let's say dark matter is such a clumpy or a lot of substructure, subhalos, and this is a beam simulation results. And galactic disk is shown in green here. And suppose some star cluster is orbiting and due to tidal interaction, the stream is appeared. So without any substructures, then the stream is very, how to say, sharp and smooth. But if there are subhalos which interact with this thin stream, then this interaction with subhalo would provide a gap because of the interaction, gravitational interaction. And this gap information provide information on the abundance of subhalos. So this is very interesting physical effect as a probe called dark matter subhalos. And next is lensing. Suppose this clumpy dark matter halo is a lens of more distant quasar, and more distant quasar is split into, for example, 4 images. Then this, due to this clumpiness of the mass distribution of the halo, the dark matter halo, the lens image, flux lens image is modified so that the flux ratio is different from that obtained from the smooth lens model. This is so-called anomalous flux ratios. And this anomalous flux ratio hardly explained by smooth lens model. For instance, this is a famous quote of the dark lens. This is a PG 1115, and this is a quasar at redshift 1.7, and redshift lens is here. The with brown is a point. Redshift is 0.3, and this white image is the lens image of the quasar, and there are 4 bright images. And there are 2 close images, so-called A1 and A2, B, C. And this number is a flux ratio with respect to the brightest one, A1. So this flux ratio is 0.59, and this is much fainter. And this kind of the lens configuration is easily reproduced through singular isothermal episode plus external shear. Probably you learned already somewhere in the summer school. So this is a model result which made by myself again many years ago. Okay, it's easily reproduced the position of the lens image like this, A1, A2, B, C, but and model this closest pair of the lens image is in principle flux ratio is 1. If one adopt a smooth lens model, so this is very solid universal phenomena or properties of the smooth lens model. Flux ratio for closest lens pair is image pair is 1. Flux ratio is 1. But observed flux ratio apparently deviate from 1. So it's so-called anomalous flux ratio. There are a lot of other effects which provide such a balance, anomalous flux ratio, such as dust extinction or micro-lensing by stars and so on. So anyway, I don't go into the detail, but this kind of the anomalous flux ratio and other lens phenomena such as effects on the extended lens images, a probe of the dark matter substructure in other galaxies. Okay, I'm done. Okay, this is the last slide for lecture 1 summary. The Milky Way is dominated by dark matter halo. Halo tracers such as Field star, Weber cluster, Sagittarius suggest total mass of the Milky Way. Basically, dark matter halo is of the order of 10 to 12 solar mass, and factor is around 1 and 2. Sagittarius stream suggests a nearly spherical sphere at this radial range, but it's not clear beyond this radius. So we need more analysis. And the flat rotation curve suggests this density distribution in the inner part where dark matter, where disk dominates. It is not clear beyond again. So we don't know yet the actual density profile in the outer part of the halo. So it's there. So, so it's important. And satellite galaxies issues. Okay, satellite galaxies basically dark matter dominated. Mass to luminous ratio is 10 to 1,000. Some faint galaxies have the mass to luminous ratio 10,000. And contrary to the CDM prediction, dark matter is core in some galaxies, the core cusp problem. Mean density is small, too big to fail problem. Total number is small, it's a missing satellite program. This sentence it's not correct, sorry. Mean density. Okay, first one is okay, but the second one is observed mean density of the spheroidal. Observed mean density of the satellite is small, sorry. And the observed total number of the satellites is small. Okay, so there are 3 programs. And this is the end of the lecture 1. And in the next lecture, lecture 2, I'd like to show some recent results related to core cusp program and missing satellite program. Okay, so that's it for lecture 1. So it's open question, comments.
Yeah. Thank you very much, Professor Chiba. Now sessions for questions. We have already 5 questions. Okay, I will ask the first question from Suzu. Can you ask your question directly, Suzu, please?
Yes, I'm here. Can you hear me?
Yes.
Yes.
Okay. I have so many questions, but yeah, it seems. Here, I just ask one question for the warming up. So let me find my question. Where it is? Oh, okay. I just wonder why the rotation velocity is increased so fast in the very center of the galaxy. Since it is obviously and then no
Milky Way.
Yeah, Milky Way or other galaxy. The rotation curve in the very center region.
Somewhere here.
Yeah, before the platform.
Yes.
Before the platform, there is a very fast increasing curve.
Yes.
Yes. Why?
Yeah, very good question. Okay, this rotation curve is assume that this curve reflects the circular rotation of the orbit of the gas or stars, but it is not the case, especially in the inner part, where, as you see, bar structure is dominant, so that basically the orbit in the inner part of the Milky Way or other galaxies as well is affected by this non-circular motion. Non-circular motion means the orbit of the stars is or gas is not circular but elongated, so that this depending on the angle between the line of sight and this bar structure, then some orbits have some angle where the velocity is higher than the nominal circular orbit. So in short, this structure is due to the basically non-axis symmetric structure of the Milky Way and other galaxies, not circular motion. So generally one should be careful to reinterpret what this plot suggests. So I said that it's a flat, but there are some disturbance, and in the outer part of the disk, sometimes there are some evidence that the disk is not flat, but it's some wavy feature, say. Deviation from the flat structure is observed, so the rotation curve also be affected. So generally, one should be careful when one interprets what this rotation curve suggests. So in short, orbit of the gas or stars is not circular generally.
Okay.
Do you understand? Yeah.
Yeah. Thank you.
Okay, thank you, Suzu. Now, next question from Raid Bani Abdu. Please directly ask the questions. Yes, okay. Please, Raid.
Good morning, Doctor.
Hello.
Good morning. Thank you for the lecture.
Welcome.
I have a question about the dark matter candidates.
Okay.
Doctor, since the all experiments have given negative results so far.
For WIMPs, yeah.
I mean that there's no exact particle that can give us the dark matter effect on
yes, I agree.
Yeah.
Yes, I agree. Yeah.
So why the scientific community don't want to agreeing to the next stage of the research process in terms of explaining the flatness of the rotation curves? I mean that why we don't take a step further in researching modified Newtonian dynamics or scalar gravitational coefficient and scalar inertial to gravitational mass ratio as well.
Yeah, I know the current state, and this is it's a kind of the one probably how to say standard way to understand dark matter. But I know that WIMP particles are not yet detected, and there are a lot of other candidates I omit in this lecture, and I just briefly mentioned in the lecture 2. So, and there are several other ways to explain the flat rotation curve and other stuff. But I haven't yet seen any alternative model which explain, say, this one. This is so beautiful. So so it's I'm not familiar with all the models, but it is very important to reproduce all this one without any how to say artificial assumption. Although there are a lot of issues in the small scale, as I show, I mentioned here and I show in lecture 2. So yeah, but I know, and as you mentioned, there are other theories. Thank you.
Thank you, Doctor. Thank you very much. Thank you.
Thank you. Maybe one more question from Dr. Miatanda. You want to ask Professor directly? Okay, yes.
Hello?
Yes.
Hello.
Hello?
Yeah.
Hello?
Yes,
Hello.
we can hear you.
Dear
Please.
Professor, I'd like to know the difference between the disk made star and halo star.
Okay, disk okay.
Yes.
Disk stars are generally having nearly circular rotation. In the cylindrical coordinates, disk stars have having, as I showed, rotation of the order of 200 kilometers per second and nearly circular rotation. But on the other hand, halo stars show random motion within the halo, and three-dimensional velocity of the halo stars is of the order of 200 kilometers per second. Again, but it's random, and it's so random motion. And halo stars say having old age of the order of 10 billion years or something. On the other hand, the disk stars are young. So halo stars are formed much before the disk formed. Yeah.
Thank you, Professor.
Okay.
Okay, thank you. Because the time is over, there are 4 more questions, Professor Chiba. I will skip to the next sessions. Is it okay?
Okay, yeah.
For the questions, there are 4 more questions.
Oh, okay.
Thank you very much, Professor Chiba, for the
Thank you.
first lectures. We will meet with Professor Chiba in the afternoon sessions. So
Okay.
stay tuned with
For
this summer school. Thank you very
4
much.
hours, 4 hours
yes,
later.
Sorry?
Yeah. 4 hours later.
Yes, 4 hours. Yes, 4 hours.
4 hours
Yeah,
later.
in Indonesian time.
4 hour Indonesian time.
Yes, later. Yes, okay.
Okay, thank you. Have a nice lunch.
4 hours in Indonesian
Lunch
time.
break.
Now it's a photo session. Now it's photo session for this lecture, Professor. Please open your camera and we'll have a photo.
Photo. Oh.
Yes, photo. Because okay, maybe Faik, you take the picture. Or Anton.
Okay.
Okay.
First slide, ready. 3, 2, 1. Wait. Yeah, second slide, ready.
Okay. Keep smile.
3, 2, 1. And then
Someone is singing.
2 more. Wait a minute. Slide. Okay, and last slide.
Okay.
Thank you for
Okay. Finish.
finish.
Okay. Thank you very much.
Thank you.
Thank you also for Professor Chiba. Then goodbye.
Okay. Goodbye. See you later. Yeah.
Okay. Goodbye. See you again.
Bye.
And see you.
Thank you, Prof.
Goodbye, Prof.
Bye.